Hello everyone, and we're back here on CodeForces. I haven't recorded a CodeForces round in quite a while. It's been probably a year since the last recorded round, or Coder in that fact. But this is a very special round, and that's why I decided to record this. It's a very special round for Blagoj. One of the writers of this round is Blagoj, so he's a frequent viewer of this channel, very great supporter and a friend of mine. And out of respect, because this is his first, I believe, his first round as a problem setter. I want to see what problems he wrote. I want to solve them and probably critique them a little bit. I hope it helps him write even better rounds in the future. And out of pure respect, for him, I want to support him in this round and to solve the problems. I haven't trained in quite a while, so this might be a kind of low performance round, and there are actually so I'm still doing ACM competitions for my faculty, and in fact we won the last round on the ACM competitions. It was a very interesting round. I'm very thankful for my team. But I'm no longer frequently competing on CodeForces or Coder. It's mainly for a couple of reasons. One is that I do not have time, and there are really other priorities and responsibilities that I have. So this I have a job, and as an engineer, as a programmer. I also study master's degree in Slovenia, so that takes a lot of my time. Also, I want to spend more time with my family and friends. I think that's one most important thing in life, if not the most important thing in life. I would say friends and family. So I want to spend more time with them. Competitions really take a lot of time from you and a lot of energy. What else? My channel is not monetized, so I cannot make this full-time job or anything like that. Even if it is monetized, I don't think the view count will be enough to get any money out of this. So out of respect for Blagoj, I will record this round, and I hope you all enjoy this round, and I hope I'll see you in the future for some other videos as well. So let's see the problems. We'll try to solve them. Okay, you're given an array of integers. An array is beautiful if there exists an array, okay, y, such that the elements of y are distinct, and the products of xi and yi is the same for all of this. That's the maximum size of subsequence of array A. This is beautiful. Why couldn't it be the whole array? A subseq. Oh yes, only the distinct elements. So wait. Okay. Because y has to be distinct. Okay, hope there's no trick with some overforcing. Okay. Okay, pass. You're given a binary string S and a typewriter with 2 buttons. Initially, your figure is on button 0. You can do the following operation: press the button on your figure that's currently on. This will type out the character that is button. Move the button to the other finger. Okay, so switch, so swap. The cost of binary string is a minimum number of operations. You need to type the entire string. Yes. So we just count the blocks, right? I think that's it. Okay, that's an easy problem. What do you mean type out the... Before typing, you may reverse at most one substring of S. Oh wow, I didn't even read the problem. More formally, you can choose indices and reverse substring as a resulting. Okay, what do I want to do here? Okay, so you want to reverse a substring of S. How do you, okay, so you always reverse somewhere where the okay, so if you start with 1, of course you want to reverse somewhere that is 0, and this will get you always. If you start with 0, you can reverse from 1 0 to from the last. So you want to make okay, so if there's 0 and 1, of course I will want to reverse them, because in this way that there's like 0 and then there's like 1. So if there is so if there is if n is bigger or equal than 2, then you gotta do this, and if s of 0 is 1 and s of 1 is 0, then I can surely reverse that and save this one. And then if s of I is 1 and s of I plus 1 is 0, I think that should be okay. But okay, so because if I reverse this character and this character, I will gain here one step and here one step. And if I have something that starts with this 1, I reverse this length to whatever that 1 is. Oh, what if I have this, right? So I reverse this and I gain here, right? Oh, so that's not that simple. So anywhere I have one set I is ss set I is equal to 1. Once if I is smaller than -1, one set I max one set I max plus 1. If this is the case, then if one set safe is one set I plus 1, then that's 2, otherwise it's 1. This was, I think, slow, but I just hope it works. It's kind of a nice problem, I would say. I think this will work. Okay, the median of an array B has written as a median. Oh, Blagoj, come on with medians. Okay. Is a small, the m variable, okay, so small, so you're given an array of integers and an integer k, you need to determine whether there exists a pair of indices LR such that smaller than k. In other words, determine whether it's possible to split an array in 3 continuous subarrays that is less than or equal to k. Interesting. Okay, pretest's passed. Okay, interesting. Oh, so n and k. And let's read that. Okay, so what is the thing here? The median is smaller than k, so the median Right, so the idea here is like, okay, so okay, let's assume that we have some element that is smaller than k, right? Can we make this element median, right? So if I choose this element as like the smallest element, right, in one array, and the other arrays is here and here, right? This will go through the first array. So actually, you can't do that. You need to choose a median that is smaller than this median in one of the arrays, and then this, and then everything else in the other. The median. So interesting. Well, that's not an easy, actually. I don't know how easy problem is that. Median of these three arrays is like the middle element. Also from L to R, yeah. So some prefix, right? For some prefix, what is the median of this prefix? And then for some other suffix, okay, what is the median of this suffix, right? And I have all of the prefixes, I have all of the suffixes. Till some this prefix, I can have this suffix, right? And what I want to do is what if I have all these medians? What if I have all these medians? This median has to be either then there's this median, right? That also makes it very hard to okay, let's say that k. So let's say that one of these medians is smaller than k, right? Let's say this median is smaller than k. We kind of technically need two medians to be smaller than k, right? Or equal than k, because median 1, median 2, and median 3, right? And now this median and this median has to be smaller than or equal than k. So either this median and this median is smaller or equal than k, then we know for sure whatever median that is, it will be. Or this median and this median, or this median and this median. So how do you combine this kind of stuff, right? Because I can have all of these medians up to some point and ask, okay, about your medians, is there some median smaller than k here? Well, what happens here? What actually happens if I get a median that is smaller than k? So there's some Okay, so there's some array, right? And let's say that I get a median that is smaller than k. Say this is smaller than k. And another number, if it comes in, it will go either on this side or on this side, right? And if it goes on this side, the median still will remain smaller than k. But if it goes on this side, the median could jump to here. So on one side, you will have some prefixes that work, right? On the other side, you will have some suffixes that actually work, right? Right? So either you find matching between the prefixes. Oh, you need for this, if this prefix works, we just need suffix from here. So if this prefix works, we just need suffix from here down that it actually works. So we don't kind of care. Yeah. So cool. Okay, so this reduced the problem to prefix on this, so monotonic prefix on this side, suffix on this side, and if something so something doesn't work, and then if it works for the whole thing from here. If something doesn't work here, and okay, so if this match, what if we have some kind of this, so it doesn't work on both sides? So what happens here? If I get an array like this and an array like this, I need to know if this median here works. So if I say the suffix is up to here, the prefix is up to here, and the suffix is up to here, this median here on this remaining array, I need to know if that median, because this works, I need to know if that median also works. That median also works. So if that median also works, let me just, okay, first let's go to the standings. Of course. Wait, what did they solve? F. Who's that guy solve F? Bitwise NOR array of k bit integers can be computed by calculating the bitwise NOR cumulatively from left to right. More formally, NOR is NOR of this and this, okay, and NOR on BI, you're given in k integers for index I, find the maximum bitwise NOR among all subarrays of I containing index. In other words, maximum value of NOR. But what is NOR? The logical NOR is both values are 0, 0 and 0. 1 if both values are 0. 1 is if both values are 0 and... Okay, I don't know. We'll see. That smells like some... I guess that smells like some FFT, but... Okay, let's see B. Let's see for the friend standings. Okay, I have cool place. Okay. Okay, so the median is so we say that if something here works, I just need this median to work in this place, in this thing here. But how? it's something. Okay, let's first, what I want to do is, let's first, no, recent atlas, and then there's like median something. There's 3 median, this thing here. There's this thing that I've wrote quite some time ago, and actually gives you like the median for a stream, right? So you just insert like all these numbers, and then you get you can get like the median, which is kind of cool. So we can do just 3 median from one side, 3 median from the other side, and okay, so we do that, but let's imagine that does not work. So let's imagine that this is the case. So from here there's no median satisfiability, then there is median satisfiability. From this side is the other way around. So the question is whether or not if I can satisfy the median here, that is smaller or equal than k, oh wait, you can't even do that, you know. I mean, no, technically one side looks like this and the other side is satisfiable, and then what if there is satisfiability here? So let's say, okay, so let's say that the one side is like this, right? And the other side, we already know that this is the case, right? So I can satisfy the median to this point, right? One of the left array. The right array, wherever I put it here, I have to know that this chunk here has median smaller than k, because I already know that this is median smaller than k, smaller or equal than k, and this is smaller or equal than k. But how do I say from here what is smaller or equal than k here? Is it some two-pointer technique? Let's see two-pointer technique. What if I say that, okay, let's imagine this. So you start an array, right? You say that the L here is up to L, and the right here is right. So because you're given an integer and you need to determine whether it exists LR such that, so LR cannot be Rn R1, and 3 continuous separate can contain deletion of several possible. Yes, so I think L and R should be existable. So let's say that both of these here and both of these cannot find the median, right? So you have some AI, B, A1, B1 here. Both of these are bigger or equal than K. And then there's some chunk here. Well, there is some median, right? but which one do you push here, right? Which one is the thing here that we want to extend? On this array, on M1 looks like M1, M2, so maybe it's better to have another C here, array C. So C1, C2, C3, C4, C5, and so on. And let's say that C3 is the median, right? So if C3 is the median, and C3 is bigger than K, we need to push the median on this side, on the smaller side than K. Because like this is the array, and now the median is here, right? And this is bigger than K. Let's say that K is here. So I want to delete from this side numbers that are bigger than K to get the median here, right? At least here. So if I want to get the median at least here, I need to delete some specific count of numbers. This count of numbers that are greater than K, right? So to get the median here. Okay. So the question is two-pointer technique, where you want always to have numbers that are bigger than you want two-pointer technique such that the numbers, if I add a number that offsets the median here to a bigger number, then I need to delete a bigger number from this side, right? Than K. And then I'm just doing a two-pointer technique, and I know that the median here just is always here, and then I can check to the left and to the right. If any one of these has the median, then that's the case. Okay, so that's probably the solution, I think, but maybe I'm too much complicating it, maybe. I'm not sure. Median left, right. Okay. What's going on here? What is this int? Mid left, mid right. Okay, and then left dot insert, and you want to insert the median AFI, and then you want net left is left dot get. You want to do that for the right side as well. Right insert A of I, mid right is right.get. Also, I want right boolean is right bool of I is whether or not median right of I is smaller or equal than k, and then if I smaller than n minus 1, right bool of I is also right bool of I plus 1. This will account for the right bool of I, or this, or this. Then you do this, and then you want to ask yourself, when it's on the left side, you want to ask yourself if median on the left from I is smaller or k, then if right bool of I plus 2, because one is this and the other is that, so I plus 2 is smaller than n, okay, and right bool at I plus 2 is this, okay, then this is yes. You can just return that. Okay, so that could be the case. This fixes the problem between these right and left, if it's right and left. But now in the middle, you need like a two-pointer technique. And okay, let's say that the right pointer is 0. How do I call this? Okay, but without any problems. Well, there has to be like 3, okay, and has to be at least 3. So the point, I can just say the right pointer is here. I can say it like this, maybe the left pointer is at 1 and the right pointer is at 1, right? And then no, let's say like this. So while right pointer is smaller than n minus 1, right pointer plus plus, now we make another stream, like let's say middle is insert a of r, right? A of r, so we insert on that middle, and then we say that we insert on that middle not sure really here. You know what could happen? So you're adding this right here, and left is smaller than r. So let's say you add one more r, and now let's say the median is not satisfied, right? It's like 2 big elements, right? So 2 bigger than k elements. So what L is going to be deleted, this element. Doesn't sit right with me. Doesn't sit right with me. So how do you, like, let's see the let's just remember the standings. I mean, let's see. Doesn't sit right with me. There's, okay, this kind of accounts for the right and the left medians, right? So if this median and this median is okay, then this median is we don't care. But now we have to account this and this, or this and this median that are smaller or equal than k. Oh, also, oh, I'm not sure if now the definition of that m divided by 2 round up is what is here. If they're both equal, yeah, I'm not sure about that, you know. We'll see. Okay, so how do you say? Yeah, let's say that I do no here. It should be more no's than yes. Exactly. And now I have to know I have to say, okay, it has to be 2.8. So let's say that this and this. So let's say that this is it's not 2.8 unique. Let's say that, okay, so you have some elements that are smaller than k, like this, right? We just want ranges where if I pick just this element, or if I pick a bunch of these elements here that are smaller than k, of course I can extend this range more. And if I pick a bunch of these elements that are closer than, if I pick all of these that are smaller than k, I can extend as twice as much of this range. So I can pick from here to here some kind of range, right? And I just need here to be a median of left, or here to be a median of right. That's the only thing I need. So I just need to extend all of these elements, all of these things, as much as I can here, right? So how do I extend? So if I have like one element, I can, if I can have one element here, right, I can take one more element and that's okay. But if I take two, so if I have one element, then I can go and take, yeah. So let's do that. Yeah, I think that's the solution. extended will be actually equal to smaller at first, and then what I can do is I can go forwards in time, and I can say extended this trick with like filling the things. So if smaller at I. No, but we need the group, right? Yeah, I don't need the fill. I just need like current. If smaller than I, current plus plus. Else like current minus minus, and then I just need that to know that if current is extended at I is where like current is bigger than not K, no. Current is bigger than 0. That's kind of really what I'm looking for, because if I find like if it's not smaller than I, then current I think that's the case. But no, that's not. Current minus minus current is max of current of 0, right? Because I never want to go below 0. Yes, I think that's the case. And I say this from the other side as well, so I just do that from the other side as well. And now that there are all of these ranges extended, what I can just say is that if it's like extended at I, if I is bigger than 0, I can just check and median left at I is at I minus 1 is bigger or is smaller or equal than K, then yeah, that's yes. If I is smaller than 1 minus 1 and median right, K also is, or no. This is not good. Oh. So first I want to print if I take these two, oh no, 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 no. I need from here to start, right? Because whatever I start from, does that make sense? Does that make sense? Yeah, I think that makes sense. No. This is correct. Okay. And this is not 6. There's 3. There's this, and these are only the 2 options. Oh, maybe it's like that. Yeah, if I take this is exactly the median, right? And I take this and I take that, but these are not the medians. So if it is extended of I, and the median of the left side is smaller or equal than k, and on the median on the right side oh yeah, of course. Makes no sense. Oh, he takes that this here is like 1. No, yeah, that's why it doesn't make any sense. This here is like, he takes this as 1 element, but it's not. Maybe we need to move this from one of the sides and then from the other of the sides. So if I have like if I have a median here starting that I take something, so the problem is that I cannot just say that this is that I'm taking. Yeah, this is like yeah. What if I started here? I can start here. So the thing is that here I need this. I need here. I need here. This here. Should only work this here should only work is current from that side, right? Okay, this apparently works. But I'm not sure. Let's try a few more cases. Let's try one case where we have three numbers. What is this here? When we have two numbers, let's say let's say like 3, that should be 0. That should be 3. That should be yes. Okay, so let's say that this is the case. It should be no. Let's add one more number. Oh, here's the thing. Let's say that this number is expected, right? So this is 1, this is 2. And this, when we take here 1 and 3, we kind of expect this, right? So 1 and 3. There's 1 and then there's 3, right? But is this the median or is this the median? Here is the m second element, m by third by second equal is okay. So the respective elements. In the fourth case, one of the representations satisfies the constraints. The respective medians are 7. Yeah, this is a smaller number. 7, 12, 3, 12, 15. So it's the smaller number of them. So the smaller number of them means that well, I think this means that this is the case. Current plus, this will get to 1, and the next thing is like, let's say that again 1. This is the median, okay. Then let's say that this is 0, then that's the median still okay. Then that's 0, that the median is not okay. Okay, let's see EX maybe. median is 8. This is smaller than 8, and this is smaller than 8, right? So the median here is still this can be okay. How is this the case? 7, 11, 7, 4, and 9. The median of the 3 array is 7, which is smaller than 7. How is 7 now the median? Wait, what? 7 is the smallest. Yeah, 7 is the smallest element. Yeah. Wow. Okay, I wasn't mistaken. Actually, this was right. I shouldn't have. I should have looked at the announcement. Looked at the announcement. The statement of the problem in Russian was okay in Russian. And note that this is the ceiling function. Returns the list. Okay. No. Okay. So 1, 1, 2, 3. Okay, this is correct. So I think this should be correct. Let's just one more time take a look at this. Right bool is going to be okay. Right bool. I think this should be okay. Please just work. Yes, I think it should work. If that works, it's amazing. That should be amazing if that works. Okay, let's see D, problem D. Oh, that's a nice. That's a long problem. Yeah, that should work. 1 hour. That's bad. An element in an array is local minimum if at least one of the following holds. This. Wait, what? Okay. So adjacent elements are bigger than it. Yeah. Similarly, an element in an array is maximum of the following. Okay. Now the local minimum maximum are not defined for arrays that only one element. Okay. There's hidden permutation P. Flanked and there are two operations that are applied to permutation P alternatively, starting from operation 1 until there is only one element left in P. Remove all elements from P which are not local minima. Remove all elements which are not local maxima. Okay. More specifically, is applied during every auto iteration, every even iteration, until there is only one element for each index. Let AI be the iteration number that PI is removed, or what is never. It can be proven that there will be only one element left in P after at most log-n iterations. You are given an array AI. Your task is to reconstruct. I knew it. I knew the like reconstruction. If that was hidden, then like of course it's reconstruction. Of course it's reconstruction. Oh. Okay. Can we get points? Can we get points? Nice. Nice. Okay. D. What is E? What was F? F was this. the NOR operation. What was the NOR if both values? So it's not OR, but guess it's some oh, okay, I don't know. Let's see the which are not -1. What does -1 means? Let AI be the iteration number that PI is removed, or -1 if it was never removed. It was never removed. One element was never removed. So if one element was never removed, then this is the last piece. And then you want to reconstruct that AI beat the iteration number. So the last iteration number, so like here 3, 1, so like the last element is what is it? 1, 2, 3, 4, 5. 5 is the last element that is removed. Then 1 it is removed. Then again, if there are multiple solutions, output any of them. So like that might not be the most optimal solution. But okay, then there is like 1, 2, 3, and 8. 3 and 8 were removed afterwards. Then these were. So in one iteration, in the first iteration, you removed all elements which are not local minima. These guys here. Oh, that 2 is local minima. Right, isn't it? Isn't 2 a local minima? Oh, not a local minima. So not a local minima means that you are removing, yeah, operation 1 is applied during every odd iteration. Operation 1 is applied during every odd iteration. And how this is removed, all of these elements? 2 and 4 and 6 and 7. The first iteration. Okay, let's see here. This is not set. In the third case, the operation permutation is for the local minima in R here, hence elements 7, 4, 8, and 5 are removed. Oh, these are the indices of the what? Wait. 7, 4, 7, 4, 8, and 5 are removed. And then these 7, 4, 8, and 5 are removed. I don't get it. Wait, what? What is the input? The input, the iteration, the number pi is removed from 1 to n. This is the iteration, that the number pi is removed. The only local minimum in 6 and 3 is 3. Thus element 6 is removed. Am I not understanding something? What? I cannot understand the input here. What's the idea here? Am I something not seeing? In the third case, operations will be applied on permutation 6, 7, 2, 4, 3, 8, 5, 1 as follows. The local minima in this 6, 2, 3, and 1. Because elements 7, 4, 8, and 5 are removed. 7, 4, 8, and 5 are removed. In the first iteration, 7, 4, this is 7, 4, 8, and 5. This is not what it is removed in the first iteration here. Rank every even iteration until there is only one element. So that big iteration. So here it makes sense. 0, 1, 2, 3, 4, 5. Makes sense. 5 to be removed last. That is 6. No idea how that happens. Is it something that is not clearly explained? What's going on here? Go minimum. How is 5 removed here on the first iteration? Okay, let's assume another case. This, in the first case of operation 3, 2, 1. Okay. As follows, the only local minima is 1. Hence the elements 2 and 3 are removed. There is only one remaining element, hence the process terminates. Okay, still I don't understand. How is this -1 here? The iteration number that pi is removed. Pi oh, okay. Whoa, I understand now. Wait. Well, this is the, Blagoj, like this is, you shouldn't have written that way. Oh, this is so unintuitive. So -1 means that this element that is here on this thing. So here this element 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 is the last element that supports. Okay. Whoa, okay. This is okay. Now we get it. Now we get it. Wow, it took me 10 minutes just to get this. 15. How many minutes did it took me to get this problem? 15, 16 minutes. What the hell? Okay, so it's fixed on the positions. So you have something like this, you know. So you have this, here is -1, this remains, this position remains. Then there is 1, 1, 1 on the first iteration, and there's like on the second iteration, and then there is on the third iteration, like that, right? So this remains on this, on that iteration. On the first iteration, these are all removed. So on the first iteration, 7, 4, 8, and 5 is removed. So these are removed. So this guy and this guy, what is remaining? This and this guy is supposed to be a local minimum, right? And it's supposed to be smaller than that guy. I mean, or local maximum, whatever. That doesn't really matter. And then these two things here should be in between these and should both not be. Well, where do you start even with this problem? Where do you start? From the beginning, from the end? Where do you start? Local minima is like that, right? And local maximum is like that. So it is guaranteed that there exists at least one permutation that satisfies array. It's guaranteed that at least one exists. It's probably something to do with like somehow you flip. Like, because if local minimum and local maximum, kind of doesn't matter where you start, right? Like, you could start at 0 and then offset it all. Well, let's start at 0, and let's say that the last element is 0. So let's say that this element is 0, right? Then this element is on the left side of this guy. So on the left side of this guy, and we know that, okay, by iterations it has to be a local minima, so this guy has to be 1. Okay, now let's take a look at these guys. These guys have to be now they have to be not local maxima, right? Yeah, they have to be not local maxima. So if they're not local maxima, that means that they cannot have like that. So this guy is on the end, this guy is like easy to determine. That guy, if it doesn't have to be local, it has to be -1, it has to be smaller than that guy. And then if that guy has to be and that guy cannot be like that, so it cannot be 2, but it must be in between, but it could be actually smaller than whatever that guy is, right? It could be also -1, right? It doesn't really matter. And then these guys should not be local minima, so this guy should be like in between these 2 guys, right? I'm not sure about what's going on here really. So of all elements that are not of all elements of P which are not local. When you're applying some, so you have seen, you're here, right, at this iteration, you're applying some ideas, right? I just need to access which of the element on the right side and which of the element on the left side is already defined. And I just need to figure out where do you put this element, in which range you put this element relative to these 2 that are already defined. My question because it could be a range of elements where you could put it. What is the best way to choose which ones? You need to know how many elements do you need to later to fill it up. What if you say the following, maybe? What if you say that, okay, for the first iteration, okay, so we know that this is 0, right? And what if, I don't know, it seems very arbitrary. What if I say that for the first iteration, because I'm not, the first iteration is not local minima, right? Not local minima. If it's not a local minima, then these are the largest elements that should be removed. Like, let's just randomly say that, okay, so let's say that this is 1. So we'll start from 1 here. Oh, stupid. Okay, let's say that this is 1. Let's start with, so there's 8 elements. 1, 2, 3, 4. Yeah, so let's start with, this is 8, this is 7, this is 5, this is 4, right? No, this is 6, this is 5. And now these are not local minima for sure. No, yeah, these are not local minima for sure, which means that, yeah, oh, I don't know which this is. I don't know if this is the last element here. I'm not sure. I'm not sure if I can know that. I think like this is only the only thing I know. This is not local minima for sure. So I remove all of these elements. And now the next iteration, which is this guy here, now I want to be sure that these are not local maximas. So whatever I do, I want them to have really small numbers. Okay. The next iteration is here, which I want to be sure that this number is not a local minima, which of course should not be. This guy is 3. So when I put the permutation here, I first delete not local minimums. So how does this look? 1, right? So this is like that. So that right? So I want to delete that are not local minimas, right? So this is not a local minima, this is not a local minima, this is not a local minima, this is not a local minima. Then I want to delete these that are not local maximum. So now it remains this, so this, delete these that are not local maximas, so this and that. Then this and that. I think that should work. Now let's hope. The only thing we can do is practically just hope. vector of we just need to sort the order. Components is like int max element of a dot begin a dot end. This is for the last component, right? Okay, and then we want to call from all of the components, and we just I mean, I don't know if that will even work. From all the components. The first iteration, like, are just very so int L is 1 and R is n minus so R is n, right? And then L so the thing is that if maximum element is divided by 2, then there's one thing, and then if the C of I is if C of I is okay, so this, then that is 0. I will just say this: if that is that case, then ptr at 0 is this is the left. That's the left pointer. Index at comc. Index at comc. That is, I need the right pointer. Permutation at that index is this. Now the maximum here is just the trick that just flips this here. Let's just check this permutation. 1 minus 1, 1 to 1. So we say 4, 2, 5, 3. 1, 4, 2, 5, 3. This is the last element. First, that are not local minima. These two elements. Oh, these are not local minima. And then they're both not local minima. The answer is 4, 3, 5. Four, 3, 5. Wait, what? Four, 3, 5, 1, 2. 4, 3, 5, 1, 2. 4, 3, 5. What is the difference between 4, 3, 5, 1, 2? These are not local minimum. So how does this graph look? This, and this is the first thing. Then this is that, then this is this. Okay. then it says the first iteration not local minima. Still doesn't really even matter this, right? 5, 3, 4. Five, 3, 4, 5, 3, 4, 1, 3. I think it's okay. Let's just submit to see if where are we wrong. Cool. So which one pretest? One was removed from the array from iteration 2, expected not to be removed at all, test case 4. I see, they're all ones, so they're all removed in iteration 1, which are not local. They're all removed. Seven, 6, 5, 1, 4. And the permutation is given 6, 5, 2, 1, 3, 4, 7. 6, 5, 2, 1, 3, 4, 7. And all of these that are not local minima, right? They're not local minima, are removed from iteration 1. Yes, that is correct here. But our representation is this, yeah. So when this is removed and all of this stuff is removed, this still remains. That is why this fails. Okay. I see. So it's something just that has to account for some other thing in this case. Smaller and bigger. Okay. Let me think it over. Just we have blocks of you have like these blocks of ones and blocks of twos. Like right here you see 5 and then there's like 1 and then there's this. The only expected output is like 1 2 3 4 5 because this has to be like all gone, all not local minima. That has to be gone. So if that has to be gone, then like then there's some trick with the blocks, which block is descending and which is as ascending, and how so, right? So what if there's like 1 and then there's 1 1 1 1 1 and then there's 2, right? So this has to be deleted in the second operation. So this guy and this guy has to be, so not local maximas are deleted, which means this has to be like that and this guy has to be like that and all of these have to be like that. So these are not local minimas. Deleted first, then not local maximums deleted second. And if there's something like that, then there's something like that also. So there's no but what if now here there is like 1 in the first iteration? So this has to be a local. No, the first iteration is what? What do we don't delete? Not local minimum. The first iteration is we don't delete local. We delete all elements that are not local minima, but this is not a local minima as well. And does that mean that this is impossible array? Could that be it? I could just like have an Is that the case that the like one of these two has to be it's very interesting. Like such a simple example and there's no way to not local. You need to delete these two, right? And then if you want to delete these two, then not local maxima, right? Also, yeah, so this is not a local maxima, nor this is the local maxima. So this is fine. This here is fine, this here is fine, it will be deleted. So not local minima will be deleted, these two. Oh, but this will be deleted in the first iteration as well, because it's not a local minima. There's no way to make this a local minima. if we make this a local minima, then this is not a local minima. So there's no way to do actually that. But what does that mean? Does that mean that there's no way to actually do any more than... There is some invariant that there is not possible. It is not possible to be done, you know. There is some invariant here, but I'm not sure what it is, you know. This thing, I think this is some kind of is it an FFT or guess something. Two to the 17. It's like 100,000. Yeah, if it's 100,000, this has to be some kind of an FFT, right? So this like the fast bit set transform or something. I'm not sure. I mean, it could be anything. Move all elements. If I add one more to it, won't change anything. If there is supposed to be not local minimum, if there is an operation, oh, it could be just like very... If there is an operation, it says remove not local minima, it means that there are some local minimas that can be set, right? So that's why he says like there's like at most half of these are local minimas. Half of these, let's say, not local minima, right? So these are local minima, so not local minimas will be removed. And then from this thing here, I need now not local maxima. So now from these guys here, I will create a not local maxima, which means that I will remove half of these, and half of this I will leave. And then not local minima again, I will create, and then I'll remove half of this, and then yeah, again and again. And that's why in lock n conditions you can make that happen. And that is why at the end there will be like this will be removed at the first condition, that was removed at the second. This would be removed actually at like some very large actual thing here, and then maybe something like the Weierstrass function. This kind of thing, something like that, like there is but like discrete var stress function. This is how this example will look like, but I'm not sure how you. I mean, I have to think about this. Like, not local minimus ones, like typical CodeForce problem, but a good one, I would say. I won't say it's a bad problem. I'd say it's a good one, but I don't like constructive problems. You know, I don't have strong opinion against constructive problems. Because it's all like pattern recognition, like you need to not local minima, and then oh, is it possible that just like from the start of the component, is it just like always like go from the middle of the no okay, we know in one component how many times we'll lose something, and now the problem is how do you say, okay, I know that these times will lose something, but how to order this something? I don't have any idea. For each of these, find where the next iteration is. Something like that. Maybe. Like, find for this where the next iteration is, and then if I didn't even read problem E, which is bad. Let's read problem E. You're given an integer k and an array a of length n, where each element satisfies some condition that is smaller or equal than k. You can perform the following operation on the array: choose two distinct integers such that this is okay, the sum. Select an integer x satisfying that x is between negative aj and decrease ai by x and increase select decrease ai by x, increase aj by x. Okay, in other words, okay, note that the constraints on X ensure that the elements A remain between 0 and K. Your task is to determine whether it is possible to make the array A non-decreasing using the buff operation. If that is possible, find the sequence of most 3 and operation that transforms array non-decreasing. Again, typical CodeForces problem. You have to probably see some pattern where in case I don't know, in case did I click? No. In case AI is bigger than AJ, blah blah blah. Non-decreasing, which means like you have to somehow switch not the required not required minimized number of operators. But I guess just there is some just technique on how you switch that. I would guess that. Okay, let's just check out maybe. Can I see now the solutions around this solve? Or again, CodeForces has this huge problem where querying one solution will take like enormous amount of time and nothing is shown until, or maybe they fixed it, I don't know. Max step starts from the max step and then it goes through all of these and then yeah, it does something like this, right, again. But if it's not SP1, I'm not sure what he does, but okay, and then from I shift to I times 2. Oh, it goes this, like it swaps. Yeah, it swaps these like in some points where it's very important and then like it swaps them in this kind of tree manner or something. Reversed. Cool. Okay. What about E? I would say it's just like edge cases or something. Yeah, you see a lot of work there. This is very bad code, but whatever. And I just want to see F for, I want to see a nice code, not like some F. He defines an operation norm, and then he joins sparse table. He uses a join sparse table, dual segment tree, and then he goes through all of these and through all of K's. Does some magic here. So wait, uses segments, the segment tree. What about the DST? Where is the DST used? No, so the DST is not even used. Oh no, the DST is used inside the segment tree to evaluate it at of 1. Interesting. No, it's not inside, it's just here, it's not a func. Or maybe it is inside. I don't know what apply does. But this is interesting, this joins sparse table. Yeah, the disjoint sparse table exactly does that thing about, and then you can query from L to R exactly on that, and after you query from L to R, he does some magic here. Okay, is that like all of the solutions? Do they use this kind of trick with? Maybe not, maybe some other thing. Okay, so let's go through the problems once again, at least those who that we solved. So the first problem was about first problem was just so I haven't practiced in a while, so that's an excuse for me. Okay, the first problem we solved it really quickly. You had to just notice that if there are two equal elements in X, there's no way to make some element Y that is going to that has to satisfy this equation, and if these two elements are the same, Y has to be also the same, but they're saying that Y has to be distinct as well to work. So you just want to count the distinct elements in X, because there you can always find some Y in order to make them all equal. So that's the whole idea in A. That's why just like set of all elements, and that's it. B was a little bit more you had this binary string, of course, and you had to move you could press the button if it's like 0 or 1, and the button is on that if your finger is on that button, but if it's on the other button you have to wait one operation to move the finger. And the whole thing was that you could actually just the whole thing is that, okay, you start at 0, right, and you don't waste operation. You only waste operation when you switch from 0 to 1. So the whole thing here is before typing, you may reverse it most to one substring of s. So if I reverse this kind of substring here, right? I don't know how do you let's say rotate this, and you reverse this substring, then you lose one operation here, and you lose one operation here, right? So you just keep this operation in between those two. So essentially, we just want to find, is there a possible way that I can reverse such a string that starts with like ones and ends with zeros, that it would combine that starting with zeros and ends with ones. And in that case, if the string is bigger than 2, so first we just sum up very naively these blocks, but then in that case you just go through all of these. You'd go from backwards to the beginning, and you just say if there is somewhere 1 that is on the left of index I. So if that's index I here, let's say that is there somewhere 1 on the left of index I that's that once array, right? And then you go from 0 to n minus 1, and if you find such a pair 1 0, then you know that you can somehow swap some subarray here. You can just reverse this subarray such that it comes 1 comes here and 0 comes here. But also we know that it doesn't matter if I'm looking at this here 1 0. I'm just taking this array as my answer essentially, but it's like invariant to that. So that's why I'm looking if there is 1 on the left side of index I, which is index I is here currently, and here I'm looking at this array here. Essentially I want to swap this array. If there is 1 somewhere here, then I can save 2 operations. If there is no 1 here, so if there's all zeros, I can only swap this here guy, and this will end here. So I only save this kind of operation here between 0 and 1, and this is the whole thing with this kind of. And then the saved operations is I'm just answer minus the save operation. This is problem B, and problem C, of course, was this median problem, which is kind of hard to explain, but essentially I don't know, like, if there could be a better solution. Of course, I mean, let's take a look at some other solutions on C. This could be better solution. Upper bound and lower bound he uses. I don't quite know what he does, but I don't even know what he does here. Okay, there are many solutions to this problem, but my solution was the following. I had 2 median streams. This is kind of a structure that I have already coded, and this structure allows me to insert a number into a stream and get the median from the stream. I think it had some lead code problem that involves this kind of structure, so I coded it and I added it to the atlas, which you can find on my GitHub, of course. And so the whole thing is that that you have 2 streams left and right, so from the left side and from the right side, and at each point I want to know what is the median, so from the left side and from the right side. And I have another right bool array that makes, so is there a median less than k on the right side of me? But okay, so I don't know how to explain. I mean, I already explained it on the stream, so I think that could be. But the left side is essentially here, and the right side is essentially here, right? So let's say that this is the left stream and this is the right stream, right? So I want to know to every point, I want to know if here there is some median which is smaller or equal than k, which starts from here. It is valid. So I assume right bool. So this right bool, if it's true here, it's true from, so it's false here, and then it's true from here, and then it's true for everything on the left here. So if I find an array that starts at 0 and ends at L, that has median less than or equal than k, and I also know that right bool is true here at this point, which means that there is an array starting at R and ending at n-1, which has median less or equal than k. It means that I have actually found a solution for this problem. I have found yes. Because I can combine this median, and I don't care about this here array. Does it have a median that is smaller or equal than k or bigger than k? That doesn't matter. So that's essentially the first part of the code. The second part of the code is a little bit more complex, and it involves essentially, okay, what happens if I want to combine some array from 0 to L that has median less than k, and I want to combine this array from L plus 1 to R minus 1 that has median less than equal than k, and now here I don't care about the median. What happens in that case? Or in the other case that I don't care about what median I have here up until L, but L plus 1 to R plus 1, I have some median that is smaller or equal than k, and from R to n-1 I have some median that is smaller or equal than k. And these two cases, so this case and this case, are essentially handled here. Here, there's two cases. The whole idea is that we want numbers that are smaller than k. So like let's just assume that this is like kind of signal. This is false and this is true, and like there are some numbers that are smaller than k, like this, right? And if I want to start it here, a subarray from L to R, I can go up to R here, that is twice this length of this signal here, right? So I can go up to here. But on the other side, if I have the same signal, if I start from R here, I can go up to L here, right? Which is twice the length, and the median will still be inside. So this is essentially what we're doing here. We're just kind of tracking the length of our array, which is current. This is kind of we have power here and then like drops here. And this is kind of we're tracking this this kind of, right? So we're extending the signal on the right side for all of these partial things, and then essentially again we're trying to see if the median on one of the side matches what again we explained here. if you kind of don't try to solve this problem on your own, it's really hard to explain, because we have two different things that we have, two different cases that we have to compute, and then on here we have even like two different median structures that we have to compute. Yeah, but D, I don't know how. I mean, I kind of know now how, but yeah, we had kind of the idea, but it was missing this trick of swapping and reversing the elements that are important. Here, this, I don't know how it looked, this thing. Yeah, he did some kind of recursion. Also, this might be a better approach, recursively, to iterate through all of these. It's an interesting choice for D that this is given, that your test, that it can be proven that there will be one element left after at most log n iterations, which might actually, I don't know, like, it's obvious if you think about it, but if you don't think about it, I don't know if it comes up. Yeah, sure, log 2 iterations, right? So given statement in the problem that AI is bounded by this, for no reason, this could have been easily up to n here. Might have made this problem even harder. But I would guess this problem was already very hard thought about this, and then like they didn't want to make it even harder. I'm not sure. But the testing seems to go a lot faster than usual. So I'm really interested. I'm kind of surprised. Yeah, I haven't been on CodeForces in quite a while, so that might explain it. But okay, that's pretty much it for today. I hope to see you actually in some other cool video, maybe computer science video instead of. I mean, CodeForces, yeah, cool and all that, but I don't believe that I have a lot of time for CodeForces or at Coder competitions currently. So yeah, thank you guys so much for watching, and I see you in the next round, or in the next video. Actually, not round.